So let's begin. In fact, we want to address two questions that are linked in this talk. Why population dynamics in a longevity conference? I think this is the main question. And the second question, which is linked, is how do birth patterns interact with mortality? And we will go through these two questions in two steps. In a first step, we will focus on the age pyramid. And as a second step, we'll focus on heterogeneity. Okay, so let's begin by the age pyramid. So you know what is an age pyramid. Here you have males, here you have females, and then you count the number of people per age class. So this is a picture of the age pyramid at time t, but of course this is evolving over time due to several demographic events. So namely for us, you have deaths in cohorts which modify the structure of the age pyramid over time, and you also have births which renews the population over time. Okay, you have also migration flows, but in this talk let us forget about migration flows. You are here in a continuous age and time setting. So age A is continuous. Sorry for A and acronym notation, but age is A for us. Sorry. Age is continuous, time is continuous, and GAT is something like the average quantity of individuals with continuous age A and continuous time T. Okay. For example, what you can do is integrate between A1 and A2, then you recover the number of people aged between A1 and A2 at time T. And for example, another example, if you are interested in intergenerational issues, I think Ragnar Norberg will talk about it later, you can compute what is called the dependency ratio, which is nothing but the number of old people divided by the number of active people, or with arbitrary ages, people above 65 divided by the number of people between 15 and 65. Okay. So if you have continuous age, continuous time, you have something you know called mortality force. And what is the role of the mortality force? Is to address how one given cohort evolves over time. Okay, at a given time nu, you have people who are born at time nu. Namely, G0 nu is the number of people with age 0 at time nu. So all people of the birth cohort nu. And so your mortality force, you know that it drives the fraction of people who survived until age A. So if you want the number of people in your cohort with age A, then you compute the fraction by multiplying your G0 nu by the survival function. Why do I show you this? Because it is the main component of a population model, but it is only the first one, and we will see the second one in a few slides. How to recover this well-known component? In fact, you differentiate in age and time this equation where GAT is given here. And so if you differentiate by age and time, you recover something which is known for many, many years in mathematical demography, which is the transport component of this McKendrick-von Foerster equation. Why transport? Because it states here that age is transported along the time axis with speed 1. And if you want a model where age evolves with speed v, then you add some little v here. Okay, so this is a crucial component of the population model, but not the only one. Okay, to go through the second main component of the population model, let us address what do we do in practice. So in practice, we want to estimate this force of mortality. But we have a big problem because there is strong statistical argument saying that it is impossible to find a non-parametric method in order to estimate the force of mortality with continuous age and continuous time. And so we are forced to assume that this force of mortality is piecewise constant. So you know that in the Lexis diagram, here you have the years, here you have age, and then you have small triangles. And on these small triangles, you assume that the force of mortality is constant. All right. And so you split your observation between integer ages A bar and integer years T bar, and you estimate the force of mortality as usual. You take the number of deaths in your small triangle, and you divide by the famous exposure to risk. Let us focus on what exposure to risk is. This is the total time lived by your individuals in the small triangle. So if you put it in equation, you can write exactly your exposure to risk as the function of the age pyramid itself. But in practice, we don't have access to the age pyramid. and we do several approximations. For example, we forget t here, and we take u equal t plus 1/2. That is, we take the population, the mid-year population, and we assume this is a good approximation of the exposure to risk. But there is quite recent work on this topic saying that there is a big problem when we estimate national indices. First remark is from Richards, which states that, in fact, there are questions when you compute population estimates for birth cohorts for which there was sharp swings in fertility. Okay. And this has been worked out by a fascinating paper by Cairns, Blake, Dodd, and Kessler, with a very nice title also, Phantoms Never Die, who proposed a methodology, in fact, to use birth patterns to compute more reliable national indices. And we will go through this to understand why, how does it work. What is the population point of view on this topic? It is very simple. A cohort has something in common, and these are the same parents. Okay, so people of a given cohort are born to the same parents, and as an equation, this is a well-known equation in demography, which is the renewal component of the equation before. And the renewal component states, okay, the unknown quantity of people born at time new is computed by summing over all possible parents of any age, and from those, take the fraction of those who gave birth. And then you have the full system of equations if you add the transport component, and this drives the evolution of the population over time. So by the way, these equations show that you can go to the human fertility database to provide more accurate estimations of mortality itself. So this is the first answer to our original questions, which is how do birth patterns interact with mortality? Okay, let us extend this in a stochastic setting, because what we do in practice is to have a stochastic population dynamics model. And in fact, it is, I will go through a little bit faster, but it is very easy to understand. It is a microscopic point of view, meaning that we don't deal with average quantities of individuals, but we deal with individuals. It works as the same. If you want to count the number of people in an age range, then you count the number of people, and you have a random integer, which is the number of people aged between A1 and A2 at time t. Well, this is a crucial point about microscopic point of view, but here this is, okay, be careful, because we call it micro-macro consistent, meaning if we have a linear model, so what we do here in practice, if you take the average number of people, then it is described by the McKendrick-von Foerster equation, which is good. But in fact, there are strong reasons, and it was in the talk by Nicole, to think that individual deaths and birth rates depend on the whole population itself. And it is a well-known demographic fact, and in this case, the average is not well described by the deterministic equation. So I don't go into details, but it is a very, very important point. Okay. Well, if you have a deterministic model, you know how to give forecast of the population. You discretize the PDE and then give forecast. You have a single trajectory. How do you do if you have some stochastic population dynamics? And in fact, it is good because it is a very easy simulation toolbox which works based on what we call the thinning algorithm. And I just take an example to show you the thinning algorithm, and then we will go through into heterogeneity. Okay, let's take a population where sample risk is quite obvious. You have 3 individuals. You start at time 0, and you have 3 individuals ordered by age. So this one is the youngest, and this one is the oldest. And I show you how the thinning algorithm works. So you want to simulate your population stochastically, and how do you do? Okay, the main tool is inspection time. So at a random times, which are inspection times, you pick an individual and then decide what happens. And we will do this. We generate a candidate time, say we pick the individual in the middle, and we decide here no event happens. Okay, no event happens, but between the 2 times population is aging. Let us do the same. We generate a candidate time, pick an individual, say the oldest, and we randomly decide that he dies. Well, a crucial point about stochastic population dynamics and inspection times is that these inspection times are closely related to those of the population itself. And so here we have only 2 individuals, one is gone, unfortunately. But then, as for demographic events, we expect to wait a little bit longer in average than before, because we have 2 individuals instead of 3. And therefore, in average, the inspection time is a bit longer. Here we do the same, pick an individual, decide no event occurs, and so on. Okay, just show you what is a burst in the model. It's just adding an individual with age 0. So here we generated this inspection time. We picked the individual on the top and decided that he gave birth. And then an individual with age 0 is added to the population. Okay, let us end this first step on the age pyramid by some simulation. So this is joint work with Séverine Arnold here, Héloïse Labillardy here also, and Nicole Caroui, of course, here also. And so we tried to do some analysis on causes of death mortality. So Héloïse Labillardy will present it this afternoon. But here, I just wanted to show you what is for us population dynamics. This graph in gray is the initial age pyramid, French age pyramid in 2008. Okay, in color, this is the final age pyramid, stochastic. But what is important to look at is the age pyramid structure. This can be measured by the dependency ratio. So here, this is the number of old people divided by the number of active people, say. And this is a dependency ratio. The important point is that this is a simulation where birth and death rates are time invariant. They only depend on age. And here what do you see is that in the first 20 years of the simulation, the age pyramid structure is strongly modified. But death and birth rates are the same. They are time invariant. And you see what is population dynamics? Population dynamics is if you define a microscopic rule which is quite simple, then you expect some abrupt changes at the population level. Okay. So let us go through heterogeneity, and also this is also based on the comments and the talk by Nicole, who states that in fact you have to look at the population at a more deeper level, which is microscopic level. So in fact, your population is composed of many subgroups which share some characteristics. So really surrogate X here is a characteristic. And you have a population model of heterogeneous population dynamics. For those people with characteristics X, you define a death rate and you define a birth rate. But if you have an heterogeneous population dynamics, this is not sufficient to do this. You have to define the rule which states how the new individuals inherit of some characteristics. So you add something which is inspired from mathematical ecology, which is a mutation kernel. Well, if you have a model with these rates, individuals would have the same characteristics during life. And you expect that individuals change their characteristics over time. So you add something which is also a demographic rate, but it is not a birth rate, it is not a death rate, but it is what we call a swap rate or a change in characteristics rate. Okay, and you also have to define some kernel to state how people change their characteristics over time. I just wanted to illustrate the impact of these characteristics changes in aggregate mortality, first by focusing on a cohort here, and with no dreams because it is a statistical example, and then propose a dream on the cohort effect at the end of the talk. So Quentin Guibert will talk in further details about multi-state models, but here I present you one simple model. You have a given age, then you are married, you get non-married, you get married, non-married, then you die. This is a multi-state model. Very simple one. Okay. And you are interested in estimating the transition intensities, mainly what's the rate to become married, to become non-married, what's the rate to die if I am married, what's the rate to die if I am non-married. And then you capture the whole multi-state dynamics. So we did some estimation on a representative sample of the French population. I don't go into details. Here, the main fact is that data is interval censored, meaning that there are censuses, and between censuses, individuals are not observed. But I just wanted to show you the result for such simple multi-state model. Okay, on the right, you have transition intensities between intermediate states. In red, transition from married to non-married. At these ages, above 60, this is mainly married to widow. So this is the age pattern of the transition rate married to widow. In black, transition rate from non-married to married. Of course, due to the age, very small probability. Okay, transition intensities are captured. Now let us capture the mortality forces. On the left, log mortality forces for in red married people, in black non-married people. And they cross. And they cross. So when we saw that, we were a bit afraid. But in fact, it is quite a well-known demographic fact, which is called the mortality compensation law. It states that if you compare two subgroups at a given time, then you expect to make it appear, meaning that if the slope is higher, the intercept is lower and reverse. Okay, and what we see here is that, of course, at these ages, mortality of married people is this one, but after a given age, this is inversed. What is the impact on aggregate mortality? If you have some understanding of the heterogeneity of your cohort, you can recompute aggregate mortality based on this cohort. So recall that in red, mortality for married people, black non-married people, and green aggregate mortality observed over time. Here you don't have the fact that mortality aggregate rejoins the lowest one because people are changing their characteristics over time. And so what you see here is that aggregate mortality is first close to the married mortality and then starts to rejoin the non-married mortality and stays at this level. But in fact, it is due to transitions from married to non-married. So you see that if you have a given cohort and an understanding of this heterogeneity, then you can have insights on the shape of aggregate mortality. Okay, so we focused on heterogeneity on a given cohort. Now let us dream about heterogeneity of the whole population. And for this, let us talk about the cohort effect, which is a well-known cohort. Which is a well-known effect in UK. So the golden cohort is people born around 1935. And we observe that they experience particular mortality improvements. Why? Let's advance some insights, interesting ones, which can be classified in three directions. This cohort experienced particular mortality improvements, so there was bad arguments for the mortality of previous and next generations. Okay, there were also good arguments for the generation we consider, the golden cohort. And you have also one remark about the patterns of birth rate. And the question is, what patterns of birth rate have to do with mortality and have to do with the cohort effect? Okay, said people born in this age range, in this year range, experience particular mortality improvements. Well, to have insights, let us have a look on birth patterns. Birth patterns are these ones, and you see that during the period in which people of the golden cohort are born, birth patterns are really unusual. In particular, they are surrounded by spikes, and in the period, they are quite low. What could be the impact of such birth patterns? I don't make any comment here, but just read the sentence by Willets, which is very important for us, which is that, in fact, one possible consequence of these rapidly changing birth rates is that the average child is likely to be different in periods where birth rates are very different. For instance, if trends in fertility vary by socioeconomic class, then the class mix of the population will change. Well, let us dream to illustrate that with a population model, you can test, simulate, and get insights on such effects. Let us define two groups. First one, quite low mortality and quite low fertility. Second group, quite high mortality, also high fertility, but reduced during a time period T1, T2. What is important here is that at the individual level in this experiment, death rates are time invariant, meaning if you look at an individual in a given group, nothing changed regarding its mortality. Let's do the experiment and simulate a sample of 10,000 individuals, split equally between the two groups, and observe aggregate fertility. This is the stylized fact we wanted to recover, is that aggregate fertility during the period T1, T2 here is low. Okay, this is natural because we expected, we made it as an input for the second group. What do we observe if we compute cohort life expectancy? We observe this one. So during the period T1, T2, life expectancy at birth is particularly high compared to previous and next periods. And so this is the stylized fact we wanted to capture. And this is to show you that, in fact, if you look at heterogeneity, you can also have an impact of birth patterns, because if you see aggregate fertility changes, then you expect something happens at the aggregate level for mortality also. Okay, so let's go back to our first question, because we dealt mainly about impact of birth patterns linked with mortality, but I wanted to give a more general overview of what we are doing in the NR project. I think such modeling framework can be seen in three directions. So first one is general mathematical model, to think jointly the things we talked about, so birth patterns, heterogeneity, this demographic stochasticity. Also, let us mention that you can include, of course, systematic risk if you take stochastic mortality models. This is a simulation toolbox, so you had a look at the simulation algorithm. And I think something which is really, really important is that it can embed various statistical inputs. In particular, you take the human mortality database, you take the human fertility database, put all this in the population model, and see what happens. Okay, so here are some references I mentioned, and I thank you for your attention.
Thank you.
Just for information, how long does it take to simulate a population of 100,000 individuals with 2 or 3 basic characteristics?
Yeah. In fact, this is a really good question, but I expected so, Gilles. So. Okay, this is quite long, because in fact, the more you have individuals, you are in a continuous time setting, and you increase the frequency as you increase the number of individuals. And so this inspection procedure is quite computer demanding. So of course, the micro consistency would allow us to first consider the deterministic behavior, and then maybe simulate, I think, the difference between the stochastic and the deterministic behavior. But I think this is further research on this topic. I hope in the lab we will address this issue.